In this research, we present a novel learning-based framework for in-betweening character movements from motion capture data. Our method utilizes phase variables to enhance the temporal coherence of generated movements and generalizes better to longer time windows between key poses. We show that our method can produce a wide range of human locomotion behaviors, crouching, crawling, aiming or jumping over long distances, and can also be applied to quadruped motions. Producing longer animation sequences by hand is tedious, and capturing each motion can be a costly process. Instead, given a sparse set of key poses, our method generates the missing motions between them in a plausible manner and can handle variable time durations between those. Various methods addressed a problem of motion in-betweening and showed promising results. However, particularly supporting longer time windows between key poses remained a challenging task and limitation of existing frameworks, typically leading to poor results in such cases. They further require more data for training in order to avoid poor generalization to unseen keyframes and transition times during inference. Our time series system utilizes a mixture of experts' neural network and predicts the character pose from one frame into the next in an auto-regressive fashion. First, we extract phase features from the unstructured movements. In order to generalize to different in-betweening durations, at each frame we sample a future target pose with a random time offset. Each set of generated weights focuses on a different motion timing while reaching the target pose. To reach a given target pose more accurately, we utilize a bidirectional control scheme that learns and predicts the motion in both target-centric and egocentric coordinates. Here we show our in-betweening workflow after training. Our work enables faster prototyping for animators to quickly generate a motion sequence from a sparse set of key poses that may have long time deltas between them. The animator can create a plausible animation by providing desired key poses and transition durations between them. The user can further interactively adjust the target frames while our model generates the movements. We evaluate our system through different ablation studies and stress tests. Without providing phase features, the character motions appears partly stiff and unnatural, especially for non-locomotion behaviors. The learned phases enable more momentum and gravity to be seen in the whole body, as the extracted phase features contain information that align the upper body as well as the lower body motion. Without the bidirectional control, the character is not reaching the target pose in time. Our system generalizes better to longer transition durations than previous methods. Only given time and target pose, the system generates a realistic trajectory towards the target. Here we show a sequence of motion between three keyframes. By modifying the timing of the keyframes, we can provide temporal variations of the motion. Since our system is temporarily conditioned by phase variables, it succeeds synthesizing correct motion even for keyframes who have very long time gaps. Note that the motion gets better the closer it reaches the target. Here, the character has to exceed a speed of 5 meters per second. Our method launches a fast forward jump to reach the goal in time. Previous techniques are failing when non-common gates between keyframes have to be performed and where the start and end frame are not within the same phase of a walking cycle. When shifting the second keyframe back, the system is forced to perform a backward walking transition. Our system extrapolates better to such extreme cases and produces less drifting because of the phase. By removing the second keyframe, we demonstrate our system to generalize better to unseen inputs than RTN, which instead floats towards the target. For many applications, it can be desirable to control the style of the motion for the in-between frames. We can control which style the neural network should generate while reaching the target pose. While RTN tends to drift towards the target, our system can produce realistic movements and transitions for actions whose dataset is not affluent, such as backward walking and sidestepping. Finally, we demonstrate our system on a quadruped character, where different locomotion modes such as walk, trot, and pace can be performed well. Thank you for watching.